Okay guys, so we're working on problem set number 6 for PH256, and this is number 1. This is the double slit experiment that you did in lab. And so I just thought I'd take you through the homework problems to help your understanding. So when we look at number 1, if we write down our givens, we know the slit separation distance. We know the distance from the slits to the screen. And we know the wavelength of the light. Okay, so that's what we're given. And then the key here is remembering the small angle approximation. So that says that theta is approximately equal to the sine of theta, which is approximately equal to the tangent of theta when theta is very small, and when theta is measured in radians. So we can see this triangle here. The tangent of theta is h1 over L, and so then we can say that the sine of theta is also h1 over L. Right, so that's the application of the small angle approximation to part A. So for part A, we just have to choose the right equation, and so looking back to your lab or your reading, we know that the condition that gives fully constructive interference, or the distance from the central maximum to any of the maxima or bright spots. So this is the central, this is the first order, this is the second order, and so we want to use d sine theta equals m lambda. And then using the small angle approximation, d times h1 over L equals 2 times lambda. And we choose m equals 2 because we're looking at the second order maximum, or this one. Okay, and so then we can figure out what h1 is if we just plug in our givens, and we get 4.06 times 10 to the negative 2 meters, or h1 equals 4.06 centimeters. So that's problem number 1A. Moving on to 1B, we're looking at h2, the distance from the central maximum to the first order minimum. And so remembering our equation, we need to choose the right one. So d sine theta equals m plus 1/2 lambda, and then applying the small angle approximation again, d times h2 over L equals 1 plus 1/2 lambda, and we chose 1 here because we're looking at the first order minimum. Okay, so now we have d times h2 over L equals 3/2 times lambda. And if you solve for h2, we get 3.04 times 10 to the negative 2 meters. Or 3.04 centimeters. So that's 1B. So remember the keys to this problem. We need to choose the right equation. So remembering this 1d sine theta equals m plus 1/2 lambda gives us the destructive interference condition, or the distance, or the angle, really, the deflection angle to the minima, or the dark spots. And the d sine theta equals m lambda gives us the condition for the maxima, or the bright spots, because that's our fully constructive interference. Okay, so number 2 is a thin film interference problem, and for thin films, the things we want to remember are we have different conditions for constructive or destructive interference due to the reflection of these light rays at these interfaces, and the path length difference that this ray travels compared to this ray. So we're really interested in the interference between these two reflected rays. So remember, we have an interface here at point 1, interface here at point 2, and a path length difference of 2L if this light is nearly normal to the interface, which in the picture it's not, but that's what we're trying to model in this picture. So we have our two thin film interference equations. And we have to choose the right one based on what's happening with the reflections and which interference pattern we want. So part A here, phase change at 0.1 due to the reflection is pi radians, or half a wavelength, because we're going from low index of refraction to high. And at 0.2, we also have another phase shift of pi radians, or half a wavelength. So if we wanted to achieve fully destructive interference, we would want another phase shift of half a wavelength, or pi radians, due to the path length difference. And so that second equation that we wrote will give us that condition. Okay, and then part E, the minimum film thickness required to give fully destructive interference. We just need to choose the correct M value. So there are a bunch of different thicknesses that would give us fully destructive interference of this particular wavelength. But we choose M equals 0, that gives us the minimum, and we apply this equation. Okay, and if we solve for L, we should get 116 nanometers. Moving on to the next part of the problem, if we wanted fully constructive interference, we would want another phase shift of a full wavelength, or 2 pi radians. And so that equation the first one that we had written down before, the 2L equals M lambda over N2, this would tell us that we get another phase shift of some integer multiple of the wavelength in that second medium, N2. And so all we need to do is apply this, and so if we want to calculate the minimum film thickness to give us fully constructive interference, we choose M equals 1. Because if we chose M equals 0 here, this wouldn't make a whole lot of physical sense. So if M equals 0, L would equal 0, so we wouldn't even have a thin film. So we choose M equals 1, and now we can apply this equation. And we should get 232 nanometers. And then for part E, that's we want the wavelength of the light in that medium. And so the wavelength of light in some medium is the wavelength of the light divided by the index of refraction of that medium. And so we have 625 nanometers divided by 1.35, and that gives us 463 nanometers. So that's part E. Okay, now number 3, the same type of question, thin film interference, but the last time we were going from low to higher index of refraction. Here we're going from low to high to low. So this is the bubble problem, if you will. So we have air, some soapy layer, and then air again. Okay, so looking at point 1, we get a phase shift of pi radians, or half a wavelength. At point 2, we get no phase shift, right? So if we go from low to high, pi, from high to low, no. So no phase shift there. So if we wanted fully constructive interference, again, we would want this path length difference to give us another phase shift of half a wavelength, so that these two light rays are back in phase with each other. Okay, so that's our m plus 1/2 equation. If we want a destructive interference, then we would want another phase shift of some full integer multiple of the wavelength, because that would keep these two rays out of phase with each other by half a wavelength. Okay, so for part E, we're told that the film thickness, the minimum thickness that gives us fully destructive interference is 221 nanometers. And so we have to apply the correct equation here. So this is the one that gives us fully destructive interference. And then we just need to choose the correct M. So M equals 1 is the minimum. And we can apply this equation. And we can solve for the wavelength. We should get 628 nanometers. And then part E, again, the wavelength in N2 is the wavelength of the light in air divided by, or vacuum, divided by N2. And so that's 628 nanometers divided by 1.42, and that gives us 442 nanometers. Okay, number 4. Number 4 is about the laser pointer in class. So much like the fake one you see on your screen. So the in-class laser pointer emits some number of photons in some time interval. And so we're given the wavelength of the light, and we want to calculate the average power, right? So just looking ahead, we know that power is energy delivered over some time interval, if we want to calculate the average power. And so we need to calculate the energy that this amount of photons delivers in this time. So looking at our equations, we know that the energy of a photon equals Planck's constant times the frequency. And we know that the speed of light is the wavelength times the frequency. So the frequency is the speed of light over the wavelength. So we can rewrite this equation as hc over lambda, or Planck's constant times the speed of light divided by the wavelength. Okay, so the energy of, this is the energy of one photon. The energy of n photons is just going to be n times hc over lambda. So now we can apply the power equation. So the power delivered by n photons is going to be n hc over lambda divided by the time interval. And so if we just put in our variables that we know, okay. So 1.39 times 10 to the 8 photons times Planck's constant in terms of joules times the speed of light, 2.998 times 10 to the 8th meters per second, divided by the wavelength in terms of meters, and all that is divided by the time interval in terms of seconds. And so keeping it in joules, we would get a watt out. So a watt is a joule per second. And so the power of this laser pointer, we get to be 4.95 times 10 to the negative 3 joules per second, or watts, and that equals 4.95 milliwatts. Okay, number 5, we are looking at a light in Yankee Stadium that emits light isotropically. And so if we kind of look at this point source of light, and it emits this light in all directions. And we want to look at the intensity at some point, and this point is some r meters away. If it's a point source and it emits light isotropically, we know the intensity of that radiation is the power of the source divided by 4 pi r squared. And this 4 pi r squared comes from that sphere of light that this point source would put out. We use the same equation with sound when we looked at the intensity of a sound source. So the intensity of this light is just the power, 1.51 times 10 to the 3 watts, divided by 4 pi times 184 meters squared. So the intensity here we get to be 3.55 times 10 to the negative 3 watts per meter squared, and that equals 3.55 milliwatts per square meter. That's number 5. Okay, number 6. Number 6 is a little complex, and I think I either screwed up the answer or I cut and pasted wrong from a previous problem. Sorry about that. So the answer here should actually be 128 watts per square meter. Okay, so let's look at this problem. So we have laser light that diverges at some angle, okay? And so if we draw a picture of this, so the laser light will actually shine in this broader circle based on that divergence angle. So we're told that this divergence angle, phi, is 1.21 degrees. And if we take this one triangle of this picture, we can redraw it. So let's call that angle theta, and theta is going to be half of phi. So theta equals 0.605 degrees. And then we have the radius of that bright spot. And then we also have what we might call L, which is the distance from the laser pointer to some screen. And so here we can apply the small angle approximation again. So if we convert 0.605 degrees to radians, we know theta is 0.01056 radians. And remembering, we talked about the small angle approximation before. So theta is approximately equal to the tangent of theta when theta is very small. So if we want to calculate, in this instance, the radius of the spot on the screen, we can do that if we say that theta is approximately equal to tan theta, which is r over L. So r would be equal to theta times L, .01056 radians times 33.3 centimeters, or 0.333 meters. Okay, so that gives us a radius of 3.52 millimeters, or 3.52 times 10 to the negative 3 meters. So that's the radius of the spot on the wall. So now for part A, we just want to calculate the area of that bright spot. So we get the area to be 3.88 times 10 to the negative 5 meters. Okay, and then part B, the intensity is the power over the area. And so we know the power of the source, 4.95 times 10 to the negative 3 watts. Let me rewrite that. Divided by the area of the spot on the screen, 3.88 times 10 to the negative 5 square meters. And that gives us an intensity of 128 watts per square meter. So laser light, we don't get that point source isotropic divergence over a 4 pi r squared sphere. Instead, it's focused more, I guess acutely would be the word. And so we can see this pretty large intensity compared to that of the light at Yankee Stadium. Okay, so number 7 is about the photoelectric effect. And in the photoelectric effect, remember we have an incident photon on some material, like some metal, and that incident photon will eject what we call a photoelectron. And that's what we apply to when we use solar panels and such. So that incident light ejects an electron. The electron can be used in a circuit to charge a battery or power your car or whatever, power your calculator. So the equation that we give you for the photoelectric effect is a statement of conservation of energy. So we give you HF, which is the energy of a photon. Energy of a photon, or HF, equals K max, which is the maximum kinetic energy of the ejected electron, plus phi, which is the work function of the material. So to calculate the speed of the fastest electrons, first I'm going to calculate the maximum kinetic energy, and then I'm going to use 1/2 mv squared to get the speed. So the first thing I'm going to do is rearrange this equation to solve for K max. So maximum kinetic energy is the energy of the photon minus phi, the work function. Okay, so I know the maximum kinetic energy of the ejected electrons, 3.53 eV. So that's in electron volts. So I know if I'm going to use this equation, kinetic energy is 1/2 mass times speed squared. I need to get this in terms of joules, because we know a joule is a kilogram times meters squared per second squared. So I'm going to convert EVs to joules. And to do that, I know that 1 electron volt is 1.602 times 10 to the negative 19 joules. Okay. So if I convert this to joules, I get 5.65 times 10 to the negative 19 joules. And so now I can sub in 1/2 mass times speed squared. Okay. And if I want to calculate the speed, okay, so the speed is 2 times the kinetic energy divided by the mass of an electron, 9.311 times 10 to the negative 31 kilograms. That's on the back of your PRC also. And so we see the speed is 1.10 times 10 to the 6 meters per second it gave you 1.11, just rounding error. Okay, so that's number 7. Okay, number 8 has to do with Compton scattering. And so I give you kind of the scenario with PET scanning. So PET is positron emission tomography, and it's used to diagnose medical conditions. It's often used in conjunction with an MRI. An MRI will give the structure of an organ, and the PET scan will give function of an organ, because what you do is you tag a pharmaceutical with some positron emitter. It's a radiopharmaceutical. You inject it in someone. That target pharmaceutical compound, that chemical compound, gets metabolized the same way that you might metabolize some other chemical compound. And so when it gets metabolized in a tumor or your heart or your brain or some organ of interest, those positrons that are emitted from that tagged drug will annihilate an electron. That annihilation gives off two 511 keV gammas that go away from each other at 180 degrees. And so we can detect those. And if we count those in coincidence, which means that we're seeing, okay, these two photons arrived from the same place and in some time window, we say that that is one event. So the computer will just tally these events, and if you tally enough of them, you can actually replicate or draw a 3D image of this organ function. So that's kind of interesting. So this is Compton scattering, but it's built in this scenario. So we'll take this part by part. So part A, we're given the energy of these photons, right? So 511 kilo electron volts. We want to calculate the wavelength of these gammas. So to do that, we can apply this equation. Energy of a photon equals Planck's constant times the frequency, or, oh, I'm sorry, this is not right. So this is HF, or we can write HC over lambda. Okay. And so I'm going to write this out because we want to talk about the unit conversion. So we're given the energy is 511 times 10 to the third eV. So H in this case is given to us in terms of joules. So 6.636 times 10 to the negative 34 joules seconds. We want to convert that right away to eV. Okay. And then C is speed of light. Over lambda. And if we solve for lambda, we should get 2.43 times 10 to the negative 12 meters. In part B, the frequency given the wavelength. So we know that C equals lambda F, and we're assuming that air is very similar to a vacuum. So the frequency is the speed of light divided by the wavelength. And so for the frequency, we get 1.23 times 10 to the 20th hertz. Okay, so part C is where we apply the Compton scattering equation that you learned. Okay, so remember Compton scattering, we have, if we model a stationary electron with some mass, and we have an incident photon. This photon has momentum because it has energy, and so what we get is we get this scattering event where this photon had some energy. Now it has some scattered energy, and this is our scattering angle theta, and then this electron might move off at some other angle with some velocity. So that's what's happening. And so we have our Compton equation, which is delta lambda equals Planck's constant divided by the mass of the target, in this case an electron, times the speed of light, times 1 minus cosine theta, which is the scattering angle. we can rewrite delta lambda as the final wavelength minus the initial wavelength. So the wavelength of the scattered photon is Planck's constant over the mass times the speed of light squared. Times 1 minus cosine theta plus that incident or initial wavelength. Okay, so let's see, plugging in the constants and the values that we know. So remember, we're told that the scattering angle is 35.5 degrees. Then we need to add the initial wavelength. And so if we do this math, we should get an answer of 2.87 times 10 to the negative 12 meters. So we get a longer wavelength for the scattered photon, and let's see if that makes sense. So let's, for part D, calculate the frequency the same way we did before. And so we get the frequency of the scattered photon to be 1.04 times 10 to the 20 hertz. Okay, so the incident photon had a higher frequency than the scattered photon, and that makes sense because frequency is related to energy. And so if we have higher frequency, we have greater energy in a photon or in light. So high energy light comes in, lower energy light comes out. So lower frequency gives us a greater wavelength. And then for part E, we're basically going backwards, right? So we want the energy of the scattered photon. We can apply this equation again. So H is Planck's constant. Again, I gave you the energy in EVs as the answer, so let's convert right away. To EVs. And so we should get, when I did this, 432 kilo electron volts. Okay, so lower energy photon that's scattered off that electron. And so we get scattering at a bunch of different angles, right? So this photon could scatter at a bunch of different angles, 90 degrees, 1 degree, 45 degrees, somewhere in the middle. We use 35.5. And you would see different wavelengths, different frequencies, and different energies of this light or of this photon at any of these scattering angles. So this 35.5 is just the one that we are interested in. So that's number 8.